Hello everyone, welcome back. This is Calculus 3. So in this video, we're going to talk about 4.7 Maxima and Minima problems. So just a little bit of recall from Calculus 1. So if you remember, one of the most useful applications for derivatives of a function of one variable is the determination of maximum and minimum values. So this application is going to apply, and in Calculus 3 again, in this case, we're going to take a look at the functions of two or more variables and how to find out the critical points using the derivative techniques. Okay, so let's just go to a little bit of a background, what you know about the critical points. Okay, so if you remember, in Calculus 1 and 2, you have a given function. It could be linear, it could be quadratic, it could be any function, but that time we've been using only the function with one variable. So let's say I have this function, right? And then we call, let's say this is a continuous function, and we call this moment, right? This is going to be local minimum. This is we call local maximum. You have another local max. So we call where the function gives you, when you take the derivative, and then it could be 0 or it could be undefined, because that moment the slope is a flat, right? So this means the slope is a 0, slope is a 0, slope is a 0, or we say slope is undefined. So we define critical points as the values of the function when the derivative equals to 0 or does not exist. So that's how you found out the critical point x. Do you remember that? So in this topic, we're gonna talk about the functions of two or more variables. So the same concept is going to be applied. Only the difference is now we're going to work with partial derivative instead of just taking the derivative of the function, because we are dealing with function of two variable. So that to find out the critical points, you are going to take the derivative, partial derivative with respect to x and y, and then make it equal to 0. And then that's the point where you can find out the critical points. So critical points could be either local maximum or local minimum, right? So that we are going to take a look at by taking the partial derivative of the function with two variables, okay? So make sure that this is the definition to find out the critical points. You're going to take the partial derivative for each and x and y and make it equal to 0. And then that's the moment x, y, you're going to find out the x and y that gives you 0 of the partial derivative. We call that as a critical point. That means you can find out the local max or local min. So let's take a look at that example, okay? So I'm going to go down slowly. So here is the example. So find the critical point. So to do that, I'm going to make a little bit of this partial derivative. We are going to find out the critical points, okay, of the function with two or more variable. So f partial derivative with respect to x is 0, or you need to find out partial derivative with respect to y is going to be 0. So that xy is going to be your critical points. So letter A. I have that, long, function of f of x comma y. Let's take the partial derivative with respect to x first, right? So first of all, we are going to take the derivative with respect to x. So this radical, I can change it to the half exponent, correct? So we can change just the radical to half exponent, okay? Now you are going to consider y as a constant, but here you are going to use the chain rule, right? because the radical is an outside function, and inside this, quadratic function has been subbed. So this is a chain rule. So I'm going to bring 1/2 to the front. So 4y second, 9x second, 24 y plus 36x plus 36, 1/2 minus 1. This is outside derivative. And then you're going to take a look at the inside derivative. So now you're going to take the derivative with respect to x, partial derivative. So y is going to be the constant. So that's going to be 0. 18x, the next one is a 0. And then 36x will be 36. 36 is going to be 0. So that's going to be inside and outside chain rule. So I'm going to write it here. Chain rule has been applied. So let me reorganize them. So 1/2, 4y second, 9x second, 24y, 36x, 36 negative 1/2, and we have a negative 18x plus 36. And then let me simplify as much as I can. So let me, divide it by 2. So 2, I'm going to multiply with them. So 2, this is going to be negative 9. This is going to be 18. So if I rewrite them, this is going to be 4y second, 9x second, 24y, 36x plus 36 to the negative 2 or 1/2. And I have a negative 9x plus 18. Are we okay? So now, what are you guys going to do? That means I can also factor out, I can find out some factor, but you can just leave it as, so this negative 1/2, I can flip. So this means we have negative 8x plus 18 in the numerator. Because of this negative, right? Because of this negative, you know that x to the negative 1/2, this is a 1/radical x. This is the same thing. So therefore, that means 4y second, 9x second, 24y, 36x plus 36. So let's leave it here. I'm not going to simplify anymore because anyway, we're going to use this. This is your partial derivative with respect to x first. Okay? One more thing, we have to find out partial derivative with respect to y. So we're going to do the same thing. Let me just copy. We have d over, in this time, dy. Right? And then we have a 1/2, right? So this is partial derivative with respect to y. So this is x, this is y. So we're going to do same thing, chain rule will be applied. So 1/2, 4y second, 9x second, 24y, 36 plus 36, 1/2 minus y, minus 1. And inside chain rule, now x is going to be the constant. So 8y minus 0 plus 24 plus 0, 0, right? So we have that. So it is going to be, again, we have here, we're going to have 8y plus 24. And you can cancel with 2. So it's going to be 4y plus 12. Am I correct? So 4y second, 9x second, 24y, 36x plus 36 to the negative 1/2, and we simplify dividing 2, 4y plus 12. So that means we have numerator 4y plus 12 with the radical, 4y second, 9x second, plus 24y, 36x, 36. So that's your partial derivative with respect to y. So now what are you going to do? Our goal is to find out the critical points where each partial derivative equal to 0. So let me make a space. So what happened? We have this copy. We have this one. And I do have partial derivative with respect to y. So we have these two solutions so far. So what happened? X and y partial derivative. This is going to be what? We're going to make it equal to 0 to find critical points of the function with two variables, correct? So what does it mean? If you do the cross multiplication, 0 is the same as a 0 over 1, correct? Are you following? So you can say negative 9x plus 18. So this equation, if you feel confused, that means you can think about it. I'm gonna just leave it at 0 is the same as a 0 over 1. So all we need to do, just make the numerator is equal to 0. So this numerator is equal to 0. Numerator, you're gonna make it equal to 0. So that's how you're going to solve for the fraction is equal to 0. Am I correct? So we're gonna solve for that. So therefore, this means the negative 9x plus 18 equal to 0 from the first partial derivative. So let me write it. So fx x comma y equal to 0 means negative 9x plus 18 equal to 0. And then the next partial derivative means the numerator is equal to 0. So you can solve for x and y. So here, negative 8x plus 18 equal to 0, x is 2. And then 4y plus 12, that means y equal to negative 3. So what does it mean? The critical points of this function is 2 comma negative 3. So at this moment, what happened? This function gonna give you either local max or local min. Does it make sense, Chia? Okay, so I'm gonna keep taking a look at more and more information. This is yours. So in this moment, so at 2 comma negative 3, the function will be either a function gonna has local max or local min. Okay, so let's take a look at more and more information. Let me actually minimize this a little bit. So now you might be wondering, Professor Ben, what should I have to do with the denominator? We're gonna work with that right now. So right now, this is a denominator. We have the same denominator. So look at that. This denominator has a radical. So in the denominator part, so denominator, so this is, we talk about the numerator. So denominator. Whatever inside of the, radical should be positive number. So you cannot have a negative number inside of the radical. So we know 4y second, negative 9x second, 24y, 36x plus 36 should be greater than or equal to 0, right? That's the require. So let me organize it. Let's organize it. So I'm going to combining same y family and x family. Y family, 4y second plus 24y. And watch me, we're going to adding and subtracting same number so that 0 plus minus that is a 0 does not affect this equation's balance. Same thing, negative. I'm going to factor out negative 9x second. And negative 36x is the same family as x, again, plus minus. And then 36, I'm going to move to the other side because that is a constant. So something you can work on like this, correct? So to find out the plus minus, let me factor out. So 4 is a factor, 4. Y second, 6y plus minus is still there. And I'm going to factor out 9, x second, 4x plus minus, and that is greater than negative 36. Are we okay? So keep thinking. Do you remember how to find out this box? So you're gonna divide it by the coefficient of y square. So that is going to be 9. So you're gonna adding 9 and 9 plus minus there. Here, -4 divided by 2 squared, so it's gonna be 4 and 4. So what does it mean? Those are 3 terms. You can find out the binomial factor. It is going to be 4. So y squared plus 6y plus 9, that is y plus 3 to the second, correct? So this blue area, they're going to be this, the second power. And now 4 times -9 will be -36 because of the distributive property 9. We have x minus 2 second power. You see that? And then -9 times -4 plus 36, that is greater than -36. So what happened? Now keep going. I'm going to reorganize it. -36 plus 36 cancel. So 4y plus 3 square, -9, x minus 2 square, that must be greater than 36. I'm going to divide it by 36 here, -36, -36 everywhere. So then what happened? -1/9 y plus 3 square, 1/4 x minus 2 square, that is greater than or equal to 2. So if you remember this equation, go to 2.4. If we have many different type of function we learned, this is actually hyperbola equation. So if you look at the equation, they're going to be something like that. So especially what happened? The center, 2 comma, at 2 comma -3 exactly, 2 comma -3. Here, you're gonna get the critical points. Exactly, we found out here. Still, we don't know whether it is a local max or local mean, but we can determine that at this moment, the slope is gonna be 0. So this is your critical points. You can actually stop there because we already found out the critical points by taking the partial derivative for each x and y and make it equal to 0. We solve for the critical points, but I really want to know more visually what that means. So I solve it by looking at the denominator. It actually gives you the hyperbola equation. So that means that 2.3, this function has either local max or local mean, and we call that particular point as a critical point. Okay, so think about the relationship. So this is how you're finding the critical points and check it. Okay, so that's a very important concept. Actually, you see the, same thing is applied between calculus 1 and 2. This is the benefit of using derivatives techniques, right? So in calculus 1, you also took the derivative to find out the critical points. And same thing, we are looking at the critical points, but in this time we're dealing with two variables function. So the partial derivative is going to be essential skill to do that. All right, so I hope this is going fine. Let's take a look at one more. There's actually letter B. So this one, actually, I'm going to bring this one all the way down. So this is, let's do B. So the equation is G. Again, this is the function with two variable, x second, 2xy, 4y second, 4x minus 6y plus 4. So let's just find out the critical points. So we are going to take partial derivative. So this is a g function with respect to x. So it is going to be d over dx. Copy, paste. So now y is going to be the constant 2x plus it's going to be 2y. This is going to be 0. This is going to be 4, 0, 0. So that must be equal to 0. Second, we have to take the partial derivative with respect to y, d over dy. So that's what it happened. So if you take the dy, 0, and then this is a 2x minus 8y, 0, negative 6. So that is going to be 2 equal to 0. So you have two equations. And then you need to solve for x and y. We're going to just work on those two equations. So we have 2x plus 2y plus 4 equal to 0. 2x negative 8y minus 6 equal to 0. This is a system of equation, isn't it? So you can solve for x and y by subtracting. So 2 minus change it to positive, plus 10 equal to 0. So y will be negative 1. You're going to plugging in 1, negative 1 into one of the equation. It should be x gives you, if you want, 2x plus negative 2y equal to negative 4. So my bad. I'm just plugging in. So it's going to be 2 times negative 2, 2x equal to negative 2x is also negative 1. So what does it mean? The critical point of this function is going to be at negative 1 comma negative. We don't know whether it's going to be local max or local min. I will show you how to determine whether these critical points give you the local min or local max of the function. But so far, this is the critical points and how to find out. Awesome, awesome, awesome. So are you ready to take a look at the next concept? Yes. So now I want to know. So critical points, as I mentioned, it gives you at that moment, you will find out either local max or local min. But how do we know that this is particularly going to give you max or min? So we have to take a look at one more step down. So that's the how to find out the local max and local min. So far, we finished the step 1. By taking the partial derivative and make it equal to 0, we were able to find out the critical points. Now, you're going to find out the discriminant. So this is another second function. You're going to find out the d value, find out the double partial derivative each x and y, and subtract xy partial derivative second power. Then, I know it sounds a little bit long, but then I'm going to go to d. Once you evaluate the d, if the d, whatever this function, we just talked about it, this is the function to give you whether the critical points, this give you the d value, give you whether the critical points is going to be local max or critical points going to local min, right? We want to know critical points, it's not enough to know whether it is a local max or local min. So to find out more specifically, to know whether your points give you local max and min, we're going to evaluate the d value. That's a d test. So by using this formula, if d is a positive, okay, that critical point is always going to give you the local max, okay? And then if the d value, actually there are two conditions going. D value is a positive, and then the second, partial derivative with respect to x is a positive, both the positive, local max. Positive, and another one is a negative, local max, local min and local max. And then if d is negative, we call, it could be not max and min, it's just settle point. And then d equal to 0, okay, we fail to find out the critical or the local max and min. So this is the 4 cases you will consider after you evaluate the d value. Okay, so one more step. We practice number 1. Okay, we know how to find out the critical points, but that's not enough, right? I want to know that critical point's going to give you local max or local min, right? Critical points, you have up and down. I want to know that whether your critical point's going to local max or local min. So how to do that? Find out the d information, d value. So a little bit of complicated formula, but we will get used to B. So by looking at the D, if D is a positive and second partial derivative with respect to both positive, okay, that's always a local mean. And the other positive negative, local max, negative saddle point, which means neither max or neither mean, okay? So this is the scenario you can determine local max and local mean of the critical points. So I'm gonna show you that example. It's not really complicated, logical thinking. You can handle it. So let's really find out the local max and local mean after you're finding the critical points, okay? Here we go. So they want to find out critical points first, and then by using the second derivative, right? Second partial derivative, these are second partial derivative with respect to x. I want to know local extrema. They want to know, what is the specific, whether they're going to give you local max or local mean. So step 1A. Step 1, we're going to find out each partial derivative. So dx, we have 4x a second. Actually, this is the same question we did it on the above, but let me just redo. 36y. So the partial derivative 8x, this is constant, will be 0, 8, and 0, 0. That must be equal to 0 to find out the critical points. And we have another one with respect to y. So d over dy, we have the same equation, copy. And then the dy, x is a constant, 18y, and then negative 36 equal to 0. So we have two equations. So from here, x is going to be negative 1. From here, y is going to be 2. So we found out the critical points. So the critical points of this function at negative 1,2, but I don't know whether it is going to be local max and local mean. I don't know. It is a local mean or local max. So let's step 2. Step 2, what happened? Second partial derivative. So this is just partial derivative to find out the critical points. Now we are going to take the second partial derivative. So we already know f of x, the partial derivative of x, 8x plus 8. I'm going to take one more time partial derivative with respect to x because we know the formula to find out the d value. If you go up, 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 this one. So let me write it. fxx, you need it. You need fyy. And then you need fx and y. And then square. Okay, so that's what I'm doing. So here, if you take one more partial derivative with respect to x, what you're going to get, it's going to be just 8, correct? And then we already know y. What you got? 18y minus 36. So the partial derivative second with respect to y, it's going to be 18. Am I correct? How about fxy? So this means you are taking the partial derivative here. We already have a y. You're taking the dx. So it means d dx of the y, which is this equation. So in this case, y is going to be the constant. You should get 0. So we have xx, yy, xy. Are you following? So that's all I got. So then we are going to copy, paste. I need to evaluate the d value. So let me minimize it. Okay. So we're going to plugging in. What happened? We have xx, we have 8 times yy, 18 minus 0 square. So you should get what? D is a 144. So we found out D value is a 144, which is, this is a positive, and your XX, which is 8, it's also positive, correct? So you have this scenario, both positive, go up, 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 up. If both positive, then that critical point is determined as a local mean. So we have, so F has a local mean, what? Where? At -1 comma here, at the critical points. So this is determined as a local mean. So we found out local mean. So that's how you are finding the, specifically whether that critical point is going to give you local max or local mean. Are you happy? Are you okay? So this is not really complicated concept at all. I already show you how to do it. Just take a look at those D tests. Okay. So then I'm not going to do the letter B. You can try the letter B. Okay. So definitely you can, it's the same strategy. Just think about it. Okay. All right. I'm going to talk about the last, concept in 4.7. So far we talked about the concept of critical point and how, local max and local min is related to the second partial derivative. The last one is, you might want to know, absolutely max and absolutely min. So let's take a look at that example. So let's say I have a specific interval. Let's say this function is not continuous. Let's say I have this. We stop here. Okay, this is the function. So as you see that, let me just move this one a little bit higher. What I'm saying is a little bit higher, lower, higher, and stop here. Okay, so what happened? This is definitely absolute max. There's no more higher than this point, correct? And then this is absolute mean. There's no more point lower than that. And these two, this is a local max, this is a local mean. These are just a local point. These are just a local. And we know that this is a higher local absolute max. We call this is absolute mean. So how to find out the absolute max and mean, and how that is related to the local max and critical points. Okay, so to find out the local max and local mean, you need a specific interval. So we call that as extreme value to find out the mean. So to find out the absolute max and mean, there should be a range, and we are going to test each point of the range. I know sounds a little bit abstract, but think about it. This is actually not really, it's, you can find out like a couple possibility, right? These are all the, the derivative is equal to 0 or undefined, but, absolute max and mean, maybe something is different from the, local max and local mean in terms of finding them. So what I'm saying is there are steps, but I'm not going to really talk about this step. Nobody going to remember and memorize it. I'm going to show you the example because I want to really emphasize on the range that is given. So this is a point, right? We don't have a guarantee that critical points is going to be equal to absolute mean or absolute max. We don't have any guarantee. Critical points can be local max and local mean. Sometimes the critical point could be, right? Sometimes it could be absolute max and mean, but how do we know that, right? So that's why finding critical points is always important, right? Finding critical points is very important, but you need to consider the boundary of the domain. What I'm saying is the range of the possible x. So let's take a look at that example. I'm going to show you so you will see what we are actually doing. So let me go down. So same type of question. In this question, I want to find out the absolute max and mean of the following function. So we have, let's say, this is the function. So you should be able to find out the critical points, but that the critical does not mean that it's always absolute max or absolute mean. We don't know yet. So if we have a specific range of x and y, within this domain and range, we are able to find out the max and mean because it's not continuous function anymore. So the function is not keep going. They're kind of like stop here. So if you have a specific range, right, you can find out, okay, that is going to be absolute max. That is going to be, local max. So to find out the absolute, max and mean, you need a domain of x and y. That's what I'm saying. That's a difference between finding local max and mean. Local max and mean can be found anything all the time, even though you have a continuous function, right? Think about it. This function is keep going in forever. But we know that this is a local max and local mean because there's going to be another, higher point and lower point all the time. So they are going to be local. But in this continuous function, we have a limitation to find out the absolute max and mean because we don't know where they're actually ending. So if you have a specific boundary of x and y, then you will be able to find out the absolute mean and max. You see that? So that's a difference. Absolute max and mean can be found when you have a specific range or boundary of x and y. So let's take a look at that example. Letter A. So first, let's find out the critical points. Step 1. So d over dx. First, I'm going to move this one a little bit here. The partial derivative with respect to x. So x is second, 2xy, 4y second, minus 4x minus 2y, 24. So x is 2x. This is going to be constant, 0, 4, and 0, 0. So that should be equal to 0. In second, we are going to the partial derivative. And I'm going to copy this. Copy, paste. So that would be 0 minus 2x, 8y, 0 minus 2. That must be equal to 0. So we're going to solve for x and y to find out the critical points. So this equation, it's going to be 2x minus 2y equal to 4. Here we have negative 2x plus 8y. I'm going to move negative to the other side too. So we have to solve for x and y. Let's adding them. Cancel 6y equal to 6. Y will be 1. And you're going to plugging in 1 into one of the equation. X should be 3. So this is the critical point. Critical point 3,1. We don't know this is going to be local mean, local max. If you want to know whether it is a local max and mean, you're going to take the second derivative, but I'm not going to do it because I'm not looking for local max and local mean. I'm looking for absolutely, max and mean. So this function that is given, we have a given function, which is this function, fx, y, right, is not continuous function, which means there are specific boundary for x and y. X is going to be between 0 and 4. Y is going to be between 2. So in this boundary, within this boundary, you have local max, local mean, you have absolute max, you have absolute mean. You will find it, right? But think about it. I'm gonna draw that boundary in the graph. So let's look at the boundary. So here we have here. So x is between 0 to 4. Okay. So let's say this line, I'm going to call this line is L1, okay? And then there's another boundary for Y2 here. So let's say this is another line L4. So I'm going to have, let's think about it. The boundary is going to be this. So we have here. So this is the boundary you can create it. This is the boundary where X is between 0 and 4, Y is between 0 and 2. So I'm going to name for each line. So let's say this is L1, and let's say this is L2, okay? And this line, let's say L3, and let's say this is L4. Okay, so I'm going to look at each line's characteristic at L1 right there. L1, I'm going to use the black color. L1 is what? From 0, 0 to 4, 0, isn't it? So what does it mean? They have the same Y. So this is actually Y equal to 0. So this line, if you want to find out the equation, L1 is going to be what? Y equal to 0. Am I correct? So what we're going to do, we have equation. We have this equation, copy. So we have this equation. I'm going to plug Y equal to 0 into the equation. So let's take a look at it. So we are going to solve it. So X squared minus 0, 0, negative 4X minus 0, 24. So that is X second minus 4X plus 24. So now I really want to know when, right? When this equation is going to be 0. So this is the flat. So hold up there. So we want to find out, so here's a little bit work. When you take the partial derivative, so let me change this one in another variable because I don't want you guys to confuse. When you take the partial derivative of this, and let's say this equation, I'm going to convert it t variable. Okay, so when you take the partial derivative x of this function in terms of t, then you can find out the moment, right, where this is going to be 0. So what I'm saying is we are going to here t squared minus 4t plus 24, a little bit smaller. I want to make it equal to 0. So we are going to take the derivative with respect to t. So here, d over dt. So 2t minus 4 equal to 0. So when t equal to 2, okay, when t equal to 2, I want to find out the value of this function. So you're going to plug in back to that. So we took the partial derivative with respect to 2, you're going to plugging in 2 into the original equation. So now f2 xy, I need a little bit space. So that 2 squared minus 2 times, 1 second, we have 2 squared. Actually, my bad. Sorry. We don't need to plug in there. So let me get rid of it. So here we have this equation, right? So you're going to plug in t equal to 2 into here. Sorry about that. So 2 squared, 4 times 2, 24. So this is a 20. Okay. We don't know what the function look like, but when y equal to 0, this function, okay, when y equal to 0 and when t equal to 2, this function has a value 20. That's what they mean. We're going to keep on doing the similar work. Just let's practice 1 second. We're going to do the same work. I'm going to just L2. L2 is from what? 4, 0 and 4, 2. So what does it mean? You have the same x variable. So that is x equal to 4. So this vertical line, we call x equal to 4. So we are going to, same work, I'm going to plug in 4 into the equation. So we have, we're going to plugging in. So if you do that work, 16 minus 2 times is 4y second. You're going to get 16, 2y plus 24. So you should get 4y second, 10y plus 24. Are we okay? So that is going to be when x equal to 4. Okay, when x equal to 4. And then now we are going to take the partial derivative with respect to t. So I'm going to change the variable for t second, just t variable. So that you're taking d over dt for t, 10t plus 24, 8t minus 10. So you're going to make it equal to 0. Now this is a partial derivative is equal to 0. T should be 5 over 4. Okay, so now we're going to plug in back into the equation here, right? So when t equal to 5 over 4, xy, 4 times 5 over 4 square minus 10 times 5 over 4 plus 24, you should get, excuse me, 17.75. So that's another possible information. So we are working on the same thing. So I'm going to just make a highlight it. I don't want to make you confused. This is L1. This is L2. Let's do 2 more, L3 and L4. So I'm going to make a little bit smaller. So L3. So L3 from where to where? So if we go to L3, 0, 2 to 4,2. So 0, 2 to 4,2. So in this time, y equal to 2. So that's the equation. So this is the equation, y equal to 2, horizontal line. So you're going to do the same work, plugging in into the equation. So if you're plugging in x second, 4x, 16, I'm just plugging in into our equation right there, the f of xy equation. And then you should get minus 4x minus 4 plus 24. So you should get x second, 8x plus 36. I'm going to convert it this t variable so that you can take the partial derivative with respect to t. So we are going to partial derivative. So it's going to be 2t minus 8. That should be equal to 0, isn't it? So you're going to solve for t is going to be 4. Again, you're going to plug in back to that equation. So when t equal to 4, this equation, 4 squared, 32 plus 36, it should be 20. So that's a 20, hold up there. So this is the L3. Last one, L4. That is a 0.0 to 0.2. So as you see that, same 0, this is x equal to 0. So this is x equal to 0. So we are going to find out the partial derivative. First, plugging in x equal to 0. So you should get everything 0 with the x. So 4y second, 2y plus 24. I'm plugging in this one into the f of xy equation. So you should get that. I'm going to convert it to the t. So that ft, at minus 2 must be equal to 0. So t should be 1 over 4. I'm going to plugging in there. So ft equal to 1 over 4. You can find out 4 times 1 over 4 squared, 2 times 1 over 4 plus 24. It is about 23.5. 75. So hold up there. Okay, you want to know what we are doing actually. So here, I evaluate each outcome of each line. So I'm going to make a little bit of space. So what does it mean so far? We found we found the value of x, fx, comma, y of each point of the boundary. That's what we just did it, which means f 0, 0, right? What happened? So if I go up here, 0, 0, 4, 0, 4, 2, 0, 2. We just evaluate the value, whether at that moment they're gonna give you max or min. So we are just to, this work. So here, f0, 0, the first corner, we found out what we got. 0, 0. So let me double check. We're gonna plugging in. So we're gonna plugging into the equation. So let me just bring this equation. Sorry, it's a little bit of long work, but we're gonna get it. So let me get rid of it. So here, so let me find out all the information. So what happened? Here, you're gonna plugging in. So that should be 0, 0, 0, 0, 0, 24, right there. And then I have to find out another points, 4, 0. We're gonna do all the work. We're gonna do 4, 0, same thing, paste. And then if you plug in 4, just plugging in 4 into x, you will get 24 again. So I'm gonna keep on going. I'm gonna actually copy this. And the next corner is a 4, 2. And then you got this one. And again, plugging in 4 and 2, I already calculate for you. And then the last one was 0, 2. So here, this is yours. We got 36. So wait. What does it mean? Okay. I'm going to show you one more thing. I'm going to bring this one actually here. I'm going to copy here, paste. Okay. So what I did, I found out the number. When x is 0, 0, your outcome is a 24 of the function. When this moment 4, 0, you got 24. Here you got 20. Here you got 36. And also we evaluate of each L1, L2, and L3. What is L1? L1, we got 20. L2, this moment your max, your value is going to be 17.75. Oh, L2 is here. 17.75. L3, what you got? We got 20. L4, we got 23.75. So out of this number, we have a couple number, 36, 20, 20, 17, 7. We evaluate all the possible outcome of each boundary and each corner. So my conclusion is here. Out of this number, the largest number, so we can find out the absolute max is going to be 36 is the largest. This is at where? 36, 0, 2. So this is the absolute max within the boundary. Within the boundary, we found out. We just test everything. Last one, absolute mean. Which one is the smallest one? 17.75 at what? This is the line. This is y, x equal to 4 line within the boundary. So this is how you're finding absolute max and mean, which is different from finding local max and local mean. So what I did, To find out the absolute max and mean, you are going to be given specific boundary. So that in this case, we have a specific equation. This is y equal to 2. This is y equal to 0, L1. L2 is x equal to 4. L4 is x equal to 0. So we evaluate what is an outcome of each, L1, L2, L3, and L4. Plus, we want to know specifically the outcome at that point, the corner points. So I evaluate the corner. These are the corner. And these are all the lines outcome. Yeah. And then comparing which one is the highest one and which one is the lowest one. So 36 is the max, absolute max at that moment, 0.2. And 17.75 is the mean at x equal to 4. That's the line L2. So that's how you're finding the absolute max. And we don't know, this is a 3-dimensional space, so you have to actually run the program to see the image. But in 2-dimensional image, we can check and we can solve it by using the derivative and partial derivative techniques. Okay, so that's all about it. So in this video, I show you how to find out the critical points, how to find out the local max and local mean, and absolute max and mean of the function when you're dealing with 2 variables. Okay, so this video is going to be pretty straightforward, so you can organize it. Again, critical points, what they mean, how to find out the local max and mean using the d-test, and then the last one, how to find out the absolute max and absolute mean by finding all the possible points and of the line. Okay, so that's all about 4.7. So you can watch more video if you need. There are embedded video in each quiz. And I really want you guys to read textbook. So I didn't do a couple questions. I skipped that. If you go to textbook, you can find out how to do letter B. So try yourself. And also there's an example, letter B. Try all the B questions. Okay, local max and absolute max and mean. And then if you have any further question, feel free to join the discussion board. That's a very active and engaging space where you can work with other people. And, you can always, get some help from there. So I think that's all about chapter 4.7. And I will stop recording at this moment. You know what to do. I will say have a, have a good rest of day. I will see you guys in the next video. Thank you, everyone. Bye-bye.